Greetings students. So today we are going to start the chapter Oscillations. Now you might be wondering, why do we need to study oscillations? Well, in our daily life we come across a lot of kind of motions, for example rectilinear motions or projectile motion. Well, these kind of motions are non-repetitive in nature. There are some other classes of motion, for example, the motion of earth around sun or swinging of child in a swing. Such kinds of motion is repetitive in nature. Well, the focus of this chapter, Oscillations, will be to understand such repetitive motions better. In this chapter, we are going to cover what is meant by periodic and oscillatory motion. Then we'll go on to understand what is meant by basic terms such as amplitude, time period, frequency, angular frequency. Then we'll understand what is displacement in the context of oscillations and how is it different from the displacement in motion. Then we'll finally touch upon what is meant by simple harmonic motions. So first thing first, let's see what is meant by periodic motion. Periodic motion is a motion which repeats itself after regular time interval. After regular interval of time. For example, imagine there is a ramp and an ant is there at the bottom of the ramp. It climbs up the ramp and it falls down. It comes back to the initial position because it does not give up. Then it again climbs up the ramp and it falls down and it comes back to the initial position again, and it repeats the motion multiple times. If you were to plot a graph of its height above the ground versus time, you would obtain a plot which will look something like this. So it climbs up, it falls down, it climbs up, it falls down, and it repeats such motion after time t. So such motion is known as periodic motion. Now let's see what is meant by oscillatory or vibratory motions. This also I'll illustrate with an example. Imagine there is a bowl and a ball is sitting at the bottom of the bowl. This ball is at rest. That means there is no external unbalanced force acting on this ball. And this point is called as equilibrium position. Now, if I were to give a small displacement to this ball, it will move in that direction and it will move away from its equilibrium position. And to counteract that, another force will start to act, which is known as restoration force. The role of this restoration force is nothing but to keep this ball at its equilibrium position, and in such way this ball will start to oscillate about this equilibrium point. Now, is there any difference between oscillation and vibration? Well, generally speaking, yes. When frequency is less, we call it oscillations. For example, a tree branch oscillates when wind blows through it. On the other hand, if frequency is high, then we call this vibration. For example, vibration of a string of a musical instrument. For example, if you strike a chord in your guitar, that will be vibrating. Now, this brings us to a key observation, that is, every oscillatory motion is periodic, but not every periodic motion is oscillatory. I'll write it down. is periodic but not every periodic motion is oscillatory. For example, if a particle is moving in a circle, sure, it is periodic, it is repeating itself after regular interval of time, but is it oscillatory? The answer is no, because it's not oscillating about any point as such. Which brings us to our next concept. Now, to understand and build our basic building blocks to understand oscillations, we need to get acquainted with its few basic terminologies. To illustrate it, what is meant by, say, amplitude, I'll give you an example. Suppose a particle is going through such a motion. This is the displacement, this is the time. So, the maximum magnitude of displacement from its mean position is called as amplitude, and it's denoted by the letter capital A. Now, what is meant by time period? Well, the smallest interval of time after which a motion repeats itself is known as time period, and it is denoted by capital letter T. Now, can you tell me what is the SI unit of time period? So, SI unit of time is second, so SI unit of time period is also second. Now, let me ask you a small question. Can you tell me what is the orbital period of Earth? Anyone? It's very simple, you know it. Okay. So, it is 365 days. As you know, Earth takes 365 days to complete one revolution around the Sun. Now let's see what is meant by frequency. Frequency is nothing but the reciprocal of time period, and it is denoted by the letter nu. Okay, it is nothing but number of repetitions per unit time. What will be the SI unit of frequency? 1 over second, since time period is second, or we can say it is second inverse, but usually we call it 1 hertz. 1 hertz equal 1 second inverse, or it equals 1 oscillation per second. Hertz was named after famous scientist Heinrich Hertz. From Germany, who was the discoverer of radio waves. So I hope now you will understand and remember what is the unit of frequency is. Now let's move on to our next topic, which we'll shortly use, which is angular frequency, omega. Angular frequency is defined as 2 pi times frequency. That quantity is angular frequency, or we can write it as 2 pi over t. Angular frequency represents rate of change of angular quantity. It is simply rate of change of angular quantity, and angular quantity is measured in radians. So the unit of omega becomes rad per second, since unit of time is second. Now let's try a simple problem. On an average, a human heart is found to beat 75 times in a minute. And we are asked to calculate its two things, frequency and secondly the time period. Now if you look carefully, this we are already given the frequency, but frequency is given per second, not per minute. So we need to simply convert this quantity into seconds. So how many seconds are in 1 minute? 60. All right. So we see minutes cancels out. So it is 75 over 60 seconds, which gives us, if we were to solve, 1.25 second inverse or 1.25 hertz. That is your frequency. Now let's try and understand let's calculate the time period. Since frequency is the reciprocal of time period, with the same logic, time period will be the reciprocal of frequency. We have got frequency as 1.25 second inverse. It will come out to be 0.8 second, the time period. So we have found the time period as well as the frequency. So we have studied a lot of new concepts. Let's move on to our next concept, which is displacement. We have already studied displacement in mechanics. Does anyone remember what was displacement in mechanics? Well, it was simply a change in position vector of a particle. Now, what is displacement in oscillations? It is change in any physical quantity with respect to time, not just position. We'll understand it better using an example. Okay. For example, there is a simple pendulum supported from a rigid support. It makes an angle theta with the vertical. So, if this angle is a function of time, then this theta also becomes your displacement variable. Okay. So let's try to describe this displacement mathematically. Displacement can be represented as a periodic function of time. Your A is your displacement, omega t is the argument. So if this argument omega t is increased with an integral multiple of 2 pi radians, we will see that the value of this function must remain same. T is given by 2 pi over omega. Thus, we observe that this function ft is periodic with time period t. Now, the same result, let us name this equation as 1. The same result is true if we were to take a sine function instead of a cosine function. Now, if we are to take a linear combination of 1 and 2, what would we get? So, ft equals a sin omega t plus b cos omega t. Now, let me substitute a as d cos phi and b as d sin phi, and let this be a and let this be b. So, substituting this in the above equation, we get d cos phi sin omega t plus d sin phi cos omega t. I will take d as common. Let me write it in a new line. We will get cos phi sin omega t plus sin phi cos omega t. There is this identity sin a cos b plus cos a sin b is sin a plus b. So, using this identity, we will get d sin omega t plus phi as ft. Now, using a and b, if we were to square and add that, we would get a square plus b square equals d square cos square phi plus sin square phi. And we know that cos square phi plus sin square phi is nothing but 1. So d becomes under root a square plus b square. If we were to divide equation b by a, we would get d sin phi over d cos phi equals b by a. That is tan phi equals b by a. That is phi equals tan inverse b by a. So we have got our phase constant and our amplitude. So we observe that any periodic function can be expressed as a superposition of sine and cosine function of different time with suitable coefficients. As a superposition of sine and cosine functions of different time with suitable coefficients. You might be wondering what I just said. So basically, if you were to take a look at this equation, it says any periodic function, this is your periodic function, can be expressed as a superposition of sine and cosine waves with different times using suitable coefficients, that is a and b. Finally, I'll discuss our final topic for today, which is simple harmonic motion. Simple harmonic motion is nothing but a periodic motion in which displacement is sinusoidal function of time. It is periodic motion in which displacement is a sinusoidal function of time. Like the equation we saw in our previous case, if it is a sine omega t plus phi, this is your equation of SHM. Sinusoidal, it might be a new fancy terms for it. It just means it vary with like a sine wave. So it will look something like this. Yeah. Okay, so that's it for today. I'll discuss the rest of the things in the next chapter. Thank you for your attention.